Space is a place of wonder and mystery, where everything is bigger, stranger, and more mind-blowing than anything we can imagine. From the blazing stars to the dark voids, the universe holds existential secrets that can leave us speechless and in deep thought. Join us as we discover them. The Cosmic Calendar. Carl Sagan, the renowned astrophysicist and science communicator, came up with an ingenious way to help people understand the immense age of the universe. He introduced the idea of the cosmic calendar. This concept compresses the entire history of the universe into a single calendar year. By doing this, it becomes easier to grasp the timeline of cosmic events and see where humanity fits within this grand scale. In the cosmic calendar, the Big Bang, which is believed to have occurred about 13.8 billion years ago, is placed at the very beginning of January 1st. This moment marks the birth of the universe, the point from which time and space began to expand. On this calendar, each second represents about 438 years, and each month about 1 billion years. This method allows us to visualize the sequence of major cosmic events within a more familiar framework. As we look at the cosmic calendar, we see that the early universe was a hot, dense state filled with energy. Gradually, it began to cool and expand. By the end of January, the first atoms started to form, primarily hydrogen and helium. These simple elements eventually clumped together under gravity's influence to form the first stars and galaxies around early February. The formation of stars was a crucial step in the evolution of the universe. Stars are like cosmic factories, fusing hydrogen and helium into heavier elements like carbon, oxygen, and iron. These elements are essential for the creation of planets and eventually life. As stars aged and exploded as supernovae, they spread these elements throughout the cosmos, seeding future generations of stars and planets with the building blocks of life. By mid-March on the cosmic calendar, the Milky Way galaxy, our home galaxy, began to form. This process took billions of years, with countless stars forming, dying, and contributing to the galaxy's growth and complexity. It wasn't until late August that our solar system started to take shape from a swirling disk of gas and dust. Around September 1st, the Earth itself was born. The early Earth was a harsh environment, but by mid-September it had cooled enough for liquid water to exist. This development was crucial for the emergence of life. Simple single-celled organisms appeared around late September, marking the beginning of life on our planet. For the next several months, these simple organisms were the dominant form of life. It wasn't until mid-December, around December 17th, that more complex life forms started to emerge. The Cambrian explosion, a period of rapid evolutionary development, saw a sudden increase in the diversity of life. Plants and animals began to colonize the land around December 20th. Dinosaurs roamed the Earth by December 25th, but they were wiped out by a massive extinction event on December 30th, paving the way for mammals to thrive. In the final hours of December 31st, human ancestors started to walk upright. Modern humans, Homo sapiens, appeared around 11:52 p.m. on December 31st. The entirety of recorded human history, from ancient civilizations to the present day, fits into the last few seconds of this cosmic year. Our technological advancements, cultural achievements, and the exploration of space all occur in this brief moment. Reflecting on human existence within this grand timeline can be both humbling and inspiring. On one hand, it shows how incredibly short our time on Earth has been compared to the age of the universe. All of human history, from the construction of the pyramids to the moon landing, represents just a tiny fraction of the cosmic timeline. This perspective can make our everyday concerns seem small and insignificant. The Fermi Paradox. The Fermi Paradox addresses one of the most intriguing questions in the search for extraterrestrial life. If intelligent alien civilizations exist, why haven't we found any evidence of them? This paradox is named after physicist Enrico Fermi, who famously asked, "Where is everybody?" during a casual conversation with colleagues in 1950. The paradox arises because given the vast number of stars and potentially habitable planets in the Milky Way galaxy alone, it seems likely that intelligent life should have emerged elsewhere. Yet, despite decades of searching, we have found no definitive signs of extraterrestrial civilizations. Along with this, if the universe is infinite, then why wouldn't we have been contacted? To understand the Fermi paradox, we need to consider the sheer numbers involved. Our galaxy, the Milky Way, contains over 100 billion stars. Many of these stars have planets orbiting them, and a significant number of these planets lie within their star's habitable zone, where conditions might be right for life to exist. If even a tiny fraction of these planets harbors life, there could be millions of civilizations out there. Given this abundance of potential homes for life, why haven't we detected any signals or signs of their existence? The Drake equation, developed by astronomer Frank Drake in 1961, provides a framework for estimating the number of active, communicative extraterrestrial civilizations in our galaxy. The equation includes several factors, such as the rate of star formation, the fraction of stars with planets, the number of habitable planets per star, the fraction of planets where life emerges, the fraction of life that becomes intelligent, the fraction of intelligent life that develops detectable technology, and the length of time such civilizations release detectable signals into space. Each term in the Drake equation is a subject of scientific inquiry and debate. While some factors, like the rate of star formation, are relatively well understood, others, such as the fraction of planets where life emerges or becomes intelligent, remain highly uncertain. By plugging different values into the equation, scientists can estimate a wide range of possible outcomes, from very few to many civilizations. However, even optimistic estimates leave us wondering why we haven't found any evidence of these civilizations. Several hypotheses have been proposed to explain the Fermi paradox. One possibility is that intelligent civilizations are extremely rare. Life might be common, but the development of intelligence and technology could be exceedingly rare events. Another hypothesis suggests that civilizations might be out there, but they are not using technologies that we can detect. For example, they might use communication methods beyond our current understanding or capabilities. Another intriguing idea is that advanced civilizations might deliberately avoid contact with us. This could be due to a variety of reasons, such as the desire to observe without interfering, known as the zoo hypothesis, or the fear of hostile encounters, leading them to remain silent. Alternatively, they might consider us too primitive to engage with, preferring to wait until we reach a higher level of technological or social development. Some scientists propose that intelligent civilizations may self-destruct before they can make their presence known to the galaxy. This idea, known as the Great Filter, suggests that there is a stage in the development of life that is extremely difficult to surpass. This stage could involve self-inflicted dangers, such as nuclear war, environmental collapse, or other catastrophic events. If the Great Filter is ahead of us, it raises sobering questions about the future of our own civilization. The search for extraterrestrial life continues through various scientific efforts. Projects like SETI, Search for Extraterrestrial Intelligence, use radio telescopes to listen for signals from other civilizations. These efforts scan the skies for patterns that might indicate intelligent communication. While no definitive signals have been detected so far, the search is ongoing, and new technologies and methods are continually being developed. Philosophically, the Fermi paradox invites us to reflect on our place in the universe. The vast silence we encounter can evoke a sense of loneliness, but it also inspires a deep sense of curiosity and wonder. If we are indeed alone, it underscores the uniqueness and preciousness of life on Earth. It challenges us to cherish and protect our planet and to seek a deeper understanding of our own existence. On the other hand, if intelligent life exists elsewhere but remains undiscovered, it pushes us to expand our search and improve our methods. The possibility of finding other civilizations offers the potential for profound insights and transformative encounters. It could revolutionize our understanding of biology, technology, and the very nature of life itself. The Fermi paradox also prompts us to consider the future of humanity. If we are to become a long-lasting civilization, capable of exploring and possibly colonizing other worlds, we must learn to overcome the challenges that threaten our survival. This includes addressing global issues such as climate change, resource depletion, and social conflicts. By solving these problems, we not only secure our future, but also enhance our ability to search for and possibly interact with other intelligent beings. The question of why we haven't encountered other civilizations remains open, and it drives much of the ongoing research in astrobiology and the search for extraterrestrial intelligence. Whether we are alone or one among many, the quest to answer this question continues to push the boundaries of human knowledge and exploration. The vast emptiness of space. When we gaze up at the night sky, the twinkling stars seem close enough to touch. However, the reality is far more astonishing. The universe is so vast that it stretches our ability to comprehend its scale. To begin to understand this immense expanse, we need to look at what scientists call the observable universe. The observable universe is the part of the entire cosmos that we can see from Earth, given the age of the universe and the speed of light. Light travels incredibly fast at about 299,792 kilometers per second, or approximately 186,282 miles per second. Yet even at this speed, it takes time for light to reach us from distant parts of the universe. The observable universe spans about 93 billion light-years in diameter. This means the light from the farthest objects we can see started its journey towards us over 13 billion years ago, not long after the Big Bang, the event thought to have created the universe. Hubble's law, named after the astronomer Edwin Hubble, helps us understand that the universe is expanding. Hubble discovered that galaxies are moving away from us, and the farther away they are, the faster they seem to be moving. This discovery was groundbreaking because it showed that the universe itself is stretching out, with space between galaxies expanding over time. Imagine dots on the surface of an inflating balloon. As the balloon inflates, the dots move further apart. This analogy helps to visualize the expansion of the universe. The implications of Hubble's law are profound. If galaxies are moving away from us, it suggests that the universe was once much smaller and denser. Rewinding time, everything converges to a single point, leading to the theory of the Big Bang. The expansion of the universe also means that the observable universe's edge is continually receding, with more of the universe becoming visible to us as time goes on. The vast emptiness of space is staggering. Between stars, galaxies, and clusters of galaxies, there are immense voids where nothing exists. No stars, no planets, just empty space. These voids can span millions of light-years. For instance, the Bootes void, one of the largest known voids, is about 330 million light-years in diameter and contains very few galaxies. This emptiness might seem like a waste of space, but it plays a crucial role in the structure and evolution of the universe. Philosophically, the vast emptiness of space can evoke a sense of wonder and insignificance. On one hand, it highlights the incredible scale of the universe and our tiny place within it. The sheer size and the emptiness between celestial objects can make one feel small and insignificant. On the other hand, it also points to the extraordinary nature of existence. Despite the vast emptiness, our planet teems with life, and we possess the unique ability to contemplate the universe's nature and our place within it. This contemplation leads to deeper philosophical questions. If the universe is so vast and mostly empty, what is our purpose within it? Are we alone, or is there other intelligent life scattered across the cosmos? These questions have fascinated humanity for centuries and continue to drive scientific inquiry and philosophical debate. The search for meaning in such an expansive and seemingly indifferent universe is a central theme in existential philosophy. Moreover, the vastness of space reminds us of the fragility of our existence. Earth, our home, is a tiny speck in an immense cosmic ocean. This perspective encourages us to appreciate and protect our planet, as it is the only known place in the universe that supports life. It also inspires us to explore and understand more about the universe. Space exploration and scientific research are not just about satisfying curiosity. They are about ensuring the long-term survival of humanity. The incomprehensible scale of the universe and the vast emptiness between celestial objects also underscore the importance of perspective. On a cosmic scale, human conflicts and concerns may seem trivial. This realization can foster a sense of unity and shared destiny among people, emphasizing that we are all part of the same small world within a grand, expansive universe. The mysteries of black holes. Black holes are among the most mysterious and fascinating objects in the universe. To understand what black holes are and how they form, we need to look at the life cycle of stars. Stars are massive balls of gas, primarily hydrogen and helium, that produce light and heat through nuclear fusion. This process occurs in their cores, where hydrogen atoms are fused into helium, releasing immense amounts of energy. When a star exhausts its nuclear fuel, its fate depends on its mass. For stars like our Sun, they will expand into a red giant and eventually shed their outer layers, leaving behind a dense core called a white dwarf. However, for stars that are much more massive, their end is far more dramatic. These stars explode in a supernova, an incredibly powerful explosion that can outshine an entire galaxy for a short time. After a supernova, the core of the massive star may collapse under its own gravity. If the core's mass is above a certain limit, nothing can stop this collapse, and it continues until a black hole is formed. A black hole is an area in space where gravity is so strong that nothing, not even light, can escape from it. The boundary surrounding a black hole is called the event horizon. Once something crosses the event horizon, it is pulled into the black hole and can never escape. Stephen Hawking, a renowned physicist, made significant contributions to our understanding of black holes. One of his most famous theories is the concept of Hawking radiation. According to quantum theory, pairs of particles are constantly being created and destroyed in empty space. Near the event horizon of a black hole, one of these particles might fall into the black hole while the other escapes. The escaping particle appears as radiation, now known as Hawking radiation. This process causes the black hole to lose mass slowly over time. Hawking's work on black holes was revolutionary because it showed that black holes are not completely black. They emit radiation and can eventually evaporate, losing all their mass and disappearing. This idea bridged the gap between quantum mechanics, which governs the behavior of tiny particles, and general relativity, which describes the behavior of massive objects like stars and black holes. Hawking's contributions have paved the way for new research and understanding in theoretical physics. The event horizon of a black hole is often used as a metaphor for the unknown and the ultimate boundary. It represents the point beyond which we cannot see or obtain information. In many ways, the event horizon symbolizes the limits of our knowledge and the mysteries that still lie beyond our understanding. Just as we cannot see beyond the event horizon, there are many aspects of the universe that remain hidden from us, waiting to be discovered. The idea of the event horizon can also be seen as a reminder of the boundaries we encounter in our quest for knowledge. It challenges us to push these boundaries and explore the unknown. Throughout history, humanity has continually expanded the frontiers of understanding, from exploring new lands to unraveling the secrets of the atom. The study of black holes and the event horizon represents another frontier, one that pushes the limits of our understanding of the universe. Black holes also raise intriguing questions about the nature of space and time. According to Einstein's theory of general relativity, the presence of a massive object like a black hole warps the fabric of space-time. This warping creates the extreme gravitational pull that characterizes black holes. As objects approach a black hole, time appears to slow down relative to an outside observer. This effect, known as time dilation, means that time behaves differently near a black hole compared to elsewhere in the universe. The mysteries of black holes also extend to their centers, known as singularities. At the singularity, the gravitational pull is so strong that it crushes matter to an infinitely small point. Our current understanding of physics breaks down at this point, and we cannot describe what happens inside a singularity. This unknown aspect of black holes makes them a rich area for scientific exploration and theoretical research. Studying black holes is challenging because they do not emit light, making them invisible to traditional telescopes. However, scientists have developed innovative ways to detect and study black holes. One method involves observing the effects of a black hole's gravity on nearby stars and gas. When a black hole pulls in matter from a companion star, the matter heats up and emits X-rays before crossing the event horizon. These X-rays can be detected by space telescopes, providing evidence of the black hole's presence. Another groundbreaking method for studying black holes involves the detection of gravitational waves. Predicted by Einstein's theory of general relativity, gravitational waves are ripples in the fabric of space-time caused by violent events like the collision of black holes. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made the first direct detection of gravitational waves from a merging black hole pair. This discovery opened a new window for observing and understanding black holes and other cosmic phenomena. The study of black holes also has implications for our understanding of the universe's fate. Some theories suggest that black holes could play a role in the ultimate end of the universe. As black holes slowly evaporate through Hawking radiation, the universe could become a cold, dark place where all matter has been swallowed by black holes or transformed into radiation. This idea, known as the heat death of the universe, presents a stark and intriguing possibility for the future of the cosmos. The multiverse theory. The multiverse theory suggests that our universe might not be the only one. Instead, it could be one of many universes, collectively known as the multiverse. This idea, which has captivated scientists and the public alike, opens up astonishing possibilities about the nature of reality and our place within it. The concept of the multiverse arises from various theories in physics and cosmology. One of the main contributors to popularizing this idea is physicist Brian Greene. Greene describes different types of multiverses, each with unique characteristics and implications. One type is the quilted multiverse, which arises from the infinite nature of space. If space is indeed infinite, then there are only so many ways matter can be arranged. Eventually, the arrangements of particles must repeat. This implies that, far beyond our observable universe, there could be other regions of space where everything is almost identical to our universe, with versions of ourselves living lives nearly identical to our own. These regions would be so far away that we could never reach them or even know of their existence directly, yet they might still be there, forming a part of the infinite cosmic quilt. Another type is the inflationary multiverse. This concept comes from the theory of cosmic inflation, which suggests that in the early moments after the Big Bang, the universe expanded at an exponential rate. Different regions of space might have stopped inflating at different times, creating bubble universes that are part of a larger multiverse. Each bubble universe could have different physical properties, different laws of physics, and different forms of life, if life exists there at all. The quantum multiverse stems from quantum mechanics, which describes the behavior of particles at the smallest scales. According to the many worlds interpretation of quantum mechanics, every possible outcome of a quantum event actually occurs, each in its own separate universe. For instance, in one universe, a particle might be in one location, while in another universe, it might be in a different location. This branching creates a vast number of parallel universes, each representing different outcomes of every event. There is also the string theory multiverse, which arises from string theory, a theoretical framework where particles are seen as tiny vibrating strings. String theory allows for the existence of multiple dimensions beyond the familiar 3 dimensions of space and 1 dimension of time. These extra dimensions could give rise to other universes with entirely different properties and structures, existing alongside our own, but in dimensions we cannot perceive. The idea of the multiverse has profound existential implications. If there are infinite universes, each with different variations of reality, it raises questions about the uniqueness and significance of our own existence. In an infinite multiverse, every possible event could happen somewhere, meaning that there could be countless versions of each of us living out every conceivable variation of our lives. This can be both mind-boggling and humbling, as it suggests that our reality is just one of an endless number of possibilities. The multiverse theory also challenges our understanding of reality and the nature of scientific inquiry. Traditionally, science seeks to explain the observable universe through empirical evidence and testable hypotheses. However, the multiverse, by its very nature, might be beyond our ability to observe directly. This raises the question of whether the multiverse theory is a scientific concept or a philosophical one. If we cannot test or observe other universes, can we consider them a part of scientific knowledge? Despite these challenges, the multiverse theory provides a rich ground for thought and exploration. It encourages us to expand our minds and consider the broader context of existence. It also connects with many deep philosophical questions about life, purpose, and reality. If there are infinite versions of ourselves, each living different lives, what does that mean for our sense of identity and free will? Are we just one of many outcomes? Or is there something inherently special about our particular universe? The possibility of multiple universes also has implications for the search for extraterrestrial life. If there are countless universes, each with different conditions and laws of physics, the chances of life existing somewhere increase dramatically. Life could take forms we cannot even imagine, thriving in environments that are entirely alien to us. The multiverse theory thus expands the scope of our search for understanding life beyond our own universe. Earth's insignificance in the cosmos. Carl Sagan, a visionary astronomer and science communicator, gave us one of the most iconic images and speeches in the history of space exploration, the pale blue dot. This term comes from a photograph of Earth taken by the Voyager 1 spacecraft in 1990. At Sagan's suggestion, NASA commanded Voyager 1, then at a distance of about 3.7 billion miles from Earth, to turn its camera back toward our planet and take a picture. In this image, Earth appears as a tiny, almost imperceptible dot, a mere fraction of a pixel in the vastness of space. In his famous speech, Carl Sagan reflected on this image, emphasizing Earth's minuscule size and its profound significance. He described how everything we know, every human being who ever lived, every moment of joy and sorrow, every discovery, every war, every act of kindness has taken place on this small stage. Sagan's words highlighted the fragility and isolation of our world, floating in the immense cosmic void. Seeing Earth from this distant vantage point offers a striking perspective. From space, national boundaries disappear, political divisions become irrelevant, and the planet is seen as a whole, a single entity. This view has a powerful impact on how we think about ourselves and our place in the universe. It underscores the unity of human experience and the shared destiny of all life on Earth. The pale blue dot image and Sagan's reflections invite us to reconsider our priorities and responsibilities. When viewed from the vastness of space, the conflicts and struggles that dominate our daily lives seem insignificant. This perspective encourages us to focus on what truly matters, the preservation and well-being of our planet and the life it sustains. It serves as a reminder that Earth is the only home we have, and its protection should be a paramount concern for all of humanity. Philosophically, the pale blue dot challenges us to think about our place in the cosmos. It reminds us of our insignificance in the grand scheme of things, but also of our unique role as the caretakers of this precious world. Our planet is a tiny, delicate speck in an unfathomably large universe, and it is our responsibility to ensure its survival for future generations. This perspective has practical implications for how we treat our environment and each other. The pale blue dot can inspire a greater sense of stewardship toward our planet. Recognizing Earth's fragility and the finite nature of its resources can motivate us to adopt more sustainable practices, reduce pollution, and mitigate the effects of climate change. It also highlights the importance of cooperation and collaboration on a global scale. The challenges we face, such as environmental degradation and resource scarcity, require collective action and a sense of shared responsibility. Furthermore, the pale blue dot serves as a humbling reminder of our limitations and the importance of humility. Despite our advancements in science and technology, we are still bound to this small planet, reliant on its ecosystems and resources. This awareness can foster a deeper respect for nature and a recognition of the interconnectedness of all life on Earth. Sagan's reflections also touch on the potential for human progress and the pursuit of knowledge. The very fact that we can capture such an image and contemplate our place in the universe is a testament to our curiosity and ingenuity. The pale blue dot symbolizes our capacity for exploration and discovery, as well as our ability to reflect on our existence and aspire to something greater. Quantum entanglement, spooky action. Quantum entanglement is one of the most fascinating and perplexing phenomena in the realm of quantum mechanics. Albert Einstein famously referred to it as spooky action at a distance, expressing his skepticism about its implications. Yet, over the years, extensive research and experimentation have confirmed that entanglement is a fundamental aspect of our universe, challenging our understanding of reality and interconnectedness on a profound level. At its core, quantum entanglement occurs when particles, such as electrons or photons, become interconnected in such a way that the state of one particle instantaneously influences the state of another, regardless of the distance separating them. This means that if two entangled particles are light years apart, a change in the state of one particle will instantly affect the state of the other. This phenomenon seems to violate the principle of locality, which states that objects are only directly influenced by their immediate surroundings. The concept of entanglement arises from the principles of quantum mechanics, which govern the behavior of particles at the smallest scales. According to quantum theory, particles exist in a state of superposition, where they can be in multiple states simultaneously until measured or observed. When two particles become entangled, their combined state is described by a single wave function, meaning their properties are intrinsically linked. Measuring the state of one particle immediately determines the state of the other, regardless of the distance between them. The phenomenon of entanglement was first discussed in the 1935 paper by Einstein, Boris Podolsky, and Nathan Rosen, known as the EPR paradox. They argued that quantum mechanics was incomplete, as it seemed to allow for instantaneous communication between entangled particles, which they believed was impossible. They suggested that hidden variables must exist, providing a more complete and deterministic explanation of quantum phenomena. However, subsequent experiments have shown that entanglement does not involve any hidden variables or faster-than-light communication. Instead, it reflects the non-local nature of quantum mechanics, where particles can be correlated in ways that classical physics cannot explain. The groundbreaking work of physicist John Bell in the 1960s provided a way to test the predictions of quantum mechanics against those of local hidden variable theories. Bell's theorem and subsequent experiments, such as those conducted by Alain Aspect in the 1980s, confirmed that the predictions of quantum mechanics were correct, and no local hidden variables could explain the observed results. The implications of quantum entanglement extend far beyond the realm of theoretical physics. Entanglement has practical applications in the emerging field of quantum information science, which includes quantum computing, quantum cryptography, and quantum teleportation. These technologies have the potential to revolutionize computing and communication, offering capabilities far beyond what is possible with classical systems. Quantum computing, for example, leverages the principles of superposition and entanglement to perform complex calculations at unprecedented speeds. In a classical computer, bits represent information as either 0 or 1. In a quantum computer, quantum bits or qubits can represent both 0 and 1 simultaneously, thanks to superposition. When qubits are entangled, the computational power of the system increases exponentially, allowing quantum computers to solve problems that are currently intractable for classical computers. This includes tasks like factoring large numbers, simulating molecular interactions for drug discovery, and optimizing complex systems. Quantum teleportation, another application of entanglement, involves the transfer of quantum information from one particle to another across a distance. While this does not mean the physical transportation of matter, it allows the state of a particle to be transmitted, effectively teleporting the information. This process relies on entangling two particles, sending one to a distant location, and then using classical communication to transfer the information. Quantum teleportation has been experimentally demonstrated over increasingly large distances, paving the way for potential advancements in quantum communication networks. Beyond these practical applications, quantum entanglement has profound philosophical and existential implications. It challenges our classical understanding of separateness and individuality, suggesting that at a fundamental level, everything in the universe is interconnected. The instant correlation between entangled particles, regardless of distance, hints at a deeper, underlying unity within the fabric of reality. This interconnectedness can be seen as a modern scientific echo of ancient philosophical and spiritual traditions that emphasize the unity and interdependence of all things. In many Eastern philosophies, such as Buddhism and Taoism, the idea of interconnectedness is central to understanding the nature of existence. Quantum entanglement provides a scientific framework that resonates with these ancient concepts, bridging the gap between science and spirituality. Moreover, entanglement forces us to reconsider the nature of information and reality itself. In classical physics, information is considered to be local and tied to specific objects. In the quantum realm, information becomes a more abstract and non-local entity, challenging our conventional notions of space and time. This shift in perspective has led some physicists to propose that information might be a fundamental building block of the universe, more basic than matter and energy. The study of entanglement also raises questions about the nature of consciousness and its role in the universe. Some theorists speculate that entanglement could provide a mechanism for understanding the interconnectedness of conscious experiences. While this idea remains speculative and controversial, it highlights the profound implications of entanglement for our understanding of mind and reality. Furthermore, the non-local nature of entanglement suggests that the universe is more holistic than previously thought. In a holistic view, the properties of the whole system cannot be fully understood by analyzing its individual parts in isolation. Instead, the system must be considered as an interconnected and interdependent whole. This perspective aligns with the principles of systems thinking and complexity science, which emphasize the importance of relationships and interactions within complex systems. In addition to its philosophical and scientific significance, quantum entanglement has inspired a sense of wonder and curiosity about the nature of the universe. It challenges us to think beyond the limitations of classical physics and explore the deeper, more mysterious aspects of reality. This sense of curiosity drives scientific inquiry and technological innovation, pushing the boundaries of what we know and can achieve. The cosmic microwave background. The cosmic microwave background, or CMB, is a faint glow of radiation that fills the entire universe. Discovered accidentally by Arno Penzias and Robert Wilson in 1965, this afterglow is a crucial piece of evidence supporting the Big Bang theory. It represents the remnants of the intense heat that filled the universe shortly after its inception. To understand the significance of the CMB, we need to go back to the very beginning, to the moment of the Big Bang. The universe started as an incredibly hot and dense point, and then rapidly expanded. In the first few moments, the universe was so hot that particles and radiation were tightly coupled, moving together as a plasma. This state lasted for about 380,000 years. During this period, the universe was opaque, much like the inside of a star, because the high-energy photons constantly interacted with electrons, preventing light from traveling freely. As the universe expanded, it cooled. When it reached a temperature of about 3,000 degrees, Kelvin, protons and electrons combined to form neutral hydrogen atoms. This process, called recombination, allowed photons to travel freely for the first time, as they no longer scattered off free electrons. The release of these photons marks the moment when the universe became transparent, and this light has been traveling through space ever since. We observe this ancient light today as the cosmic microwave background. The discovery of the CMB provided strong evidence for the Big Bang theory. Before its detection, there were competing models for the origin of the universe, including the steady-state theory, which posited that the universe has always existed in a constant state without a beginning. The uniform and pervasive nature of the CMB strongly supported the idea that the universe originated from a single, highly energetic event. The CMB is incredibly uniform, with slight fluctuations that represent the seeds of future structures like galaxies and clusters of galaxies. Scientists have studied the CMB in great detail using satellites like the Cosmic Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite. These missions have mapped the temperature fluctuations in the CMB with increasing precision. The tiny variations in temperature, only a few millionths of a degree, provide a snapshot of the early universe's conditions. By analyzing these fluctuations, scientists have gained insights into the universe's composition, age, and the processes that led to the formation of large-scale structures. The CMB also has a characteristic spectrum known as a blackbody spectrum, which is a perfect match for the predictions of the Big Bang theory. This spectrum shows that the CMB is not just random noise, but the cooled remnants of the intense heat that once filled the universe. The temperature of the CMB today is about 2.7 degrees Kelvin, just above absolute zero, indicating how much the universe has expanded and cooled since its beginning. The significance of the CMB extends beyond confirming the Big Bang theory. It serves as a cosmic relic, an echo from the early universe that provides a wealth of information about the conditions at that time. By studying the CMB, scientists have determined that the universe is about 13.8 billion years old. They have also learned about the relative amounts of different types of matter and energy, including dark matter and dark energy, which make up most of the universe's content. The CMB's discovery and subsequent studies have revolutionized our understanding of cosmology. It has allowed us to reconstruct a detailed history of the universe, from the moments immediately following the Big Bang to the formation of the first atoms, stars, and galaxies. It has also provided critical tests for our theories of physics under extreme conditions, offering a window into the fundamental laws that govern the universe. One of the most fascinating aspects of the CMB is its role in revealing the universe's large-scale structure. The tiny fluctuations in the CMB's temperature are the imprints of quantum fluctuations from the very early universe, magnified by cosmic inflation. These initial irregularities served as the seeds for the gravitational collapse that led to the formation of galaxies, stars, and ultimately the complex structures we observe in the universe today. The CMB also highlights the interconnectedness of different scientific fields. Its study combines elements of astrophysics, particle physics, and general relativity, demonstrating how advances in one area can inform and enhance our understanding in others. For instance, the precise measurements of the CMB have provided stringent tests for the theory of inflation, which posits a rapid expansion of the universe immediately after the Big Bang. The success of these tests has helped solidify inflation as a cornerstone of modern cosmology. Furthermore, the study of the CMB has led to the development of new technologies and methodologies. The sensitive instruments used to measure the CMB's tiny temperature fluctuations have pushed the boundaries of what is technologically possible, driving advancements in detector technology, data analysis techniques, and our ability to observe the universe with unprecedented precision. The cosmic microwave background serves as a poignant reminder of our quest to understand the universe's origins and our place within it. It connects us to the very beginning of time, offering a glimpse into the conditions that shaped the cosmos we inhabit. As we continue to probe the CMB's secrets, we not only learn more about the universe's past, but also gain insights that could shape our future explorations. The strange nature of time. Albert Einstein's theory of relativity, introduced in the early 20th century, revolutionized our understanding of time and space. This theory consists of two main parts: special relativity and general relativity. Special relativity, published in 1905, focuses on objects moving at constant speeds, particularly those nearing the speed of light. General relativity, introduced in 1915, extends these ideas to include acceleration and gravity. One of the most astonishing aspects of special relativity is the concept of time dilation. According to this theory, time is not a fixed, universal constant. Instead, it is relative and can vary depending on an observer's speed. As an object approaches the speed of light, time appears to slow down for that object relative to an observer at rest. This effect, known as time dilation, has been confirmed through numerous experiments and observations. To illustrate time dilation, imagine a spaceship traveling at a speed close to the speed of light. To the passengers on the spaceship, time would seem to pass normally. However, to an observer on Earth, the clocks on the spaceship would appear to tick more slowly. If the spaceship traveled at near light speed for what felt like a year to its passengers, many years could have passed on Earth by the time the spaceship returned. This phenomenon highlights the strange and counterintuitive nature of time as described by special relativity. The effects of time dilation are not just theoretical, they have practical implications and have been observed in various experiments. One famous example involves particles called muons, which are created when cosmic rays strike the Earth's atmosphere. Muons have a very short lifespan, decaying in microseconds. However, muons traveling at speeds close to the speed of light reach the Earth's surface because time dilation extends their lifespan from our perspective on Earth. Without time dilation, these particles would decay long before reaching the ground. General relativity extends the concept of relativity to include gravity. According to general relativity, massive objects like stars and planets warp the fabric of spacetime, creating what we perceive as gravity. This warping of spacetime also affects the passage of time. Clocks closer to a massive object, like a planet or a star, tick more slowly compared to those farther away. This effect is called gravitational time dilation. An example of gravitational time dilation can be seen with GPS satellites orbiting the Earth. These satellites experience less gravitational pull than clocks on the Earth's surface, causing them to tick slightly faster. Engineers must account for this difference in time to ensure the accuracy of GPS systems. If they did not, the small time discrepancies would accumulate, leading to significant errors in positioning. The concept of time as a relative phenomenon has profound philosophical implications. Traditionally, time has been viewed as a constant, flowing uniformly for everyone. Einstein's theory challenges this notion, suggesting that time is fluid and dependent on the observer's frame of reference. This idea prompts us to rethink our understanding of time and its role in the universe. One philosophical implication of time dilation and relativity is the idea that time is not an absolute backdrop against which events occur. Instead, it is intertwined with space, forming a four-dimensional fabric known as space-time. This fabric can be stretched, compressed, and warped by mass and energy, affecting how we experience time. This view of time as interconnected with space shifts our perception from a linear, fixed timeline to a dynamic and flexible continuum. Relativity also raises questions about the nature of simultaneity. In our everyday experience, we assume that events happening at the same time are simultaneous for everyone. However, according to special relativity, simultaneity is relative. Two events that appear simultaneous to one observer may occur at different times for another observer, moving at a different speed. This relativity of simultaneity challenges our intuitive understanding of time and causality. The realization that time can be experienced differently depending on speed and gravity has led to fascinating thought experiments and science fiction scenarios. One well-known example is the twin paradox. In this scenario, one twin travels on a high-speed journey through space while the other remains on Earth. Due to time dilation, the traveling twin ages more slowly and returns to find their sibling much older than themselves. While this is a theoretical example, it illustrates the dramatic effects that high-speed travel can have on time. Einstein's theories also invite us to consider the broader implications of living in a universe where time is not a fixed constant. If time can be stretched and compressed, it suggests that our experience of the past, present, and future is not as straightforward as we might think. This perspective can influence how we think about history, memory, and the future. It encourages us to view time not just as a sequence of events, but as a dimension that interacts with space and matter. The idea of time as relative also connects to deeper existential questions about the nature of existence and our place in the universe. If time is not absolute, what does that mean for our understanding of reality? How do we reconcile our everyday experiences with the strange and complex nature of time revealed by relativity? These questions inspire ongoing exploration and reflection, both in science and philosophy. In practical terms, the understanding of time dilation and relativity has led to significant technological advancements. Besides the GPS systems already mentioned, technologies such as particle accelerators, which study subatomic particles at high speeds, rely on principles of relativity. These accelerators have contributed to breakthroughs in physics, medicine, and materials science. Discovering other worlds. The search for exoplanets, or planets outside our solar system, has captured the imagination of scientists and the public alike. These distant worlds offer the tantalizing possibility of discovering life beyond Earth and understanding more about the formation and diversity of planetary systems. The techniques used to discover these planets are sophisticated and have led to significant breakthroughs in our quest to find other worlds. One of the primary methods used to discover exoplanets is the transit method. This technique involves observing the light from a star and looking for periodic dimming, which indicates that a planet is passing or transiting in front of the star. As the planet moves across the star, it blocks a small fraction of the star's light, causing a slight dip in brightness. By measuring these dips, scientists can determine the planet's size and orbit. The transit method has been incredibly successful, particularly with the help of space telescopes like Kepler, which has discovered thousands of exoplanets using this technique. Another important method is the radial velocity method, also known as the Doppler method. This technique measures the tiny wobbles in a star's motion caused by the gravitational pull of an orbiting planet. As a planet orbits a star, it exerts a gravitational force on the star, causing it to move in a small orbit or wobble. This wobble affects the light emitted by the star, causing shifts in its spectral lines due to the Doppler effect. By analyzing these shifts, scientists can infer the presence of a planet, as well as its mass and orbit. The radial velocity method has been instrumental in confirming the existence of many exoplanets. Among the significant discoveries made using these techniques is Kepler 186f, an exoplanet located about 500 light-years away in the constellation Cygnus. Discovered by the Kepler Space Telescope in 2014, Kepler 186f is notable because it is the first Earth-sized planet found in the habitable zone of its star. The habitable zone, sometimes called the Goldilocks zone, is the region around a star where conditions might be just right for liquid water to exist, which is crucial for life as we know it. Kepler 186f's discovery raised hopes that there might be many Earth-like planets in our galaxy, potentially harboring life. Another remarkable discovery is Proxima Centauri b, an exoplanet orbiting the closest star to our solar system, Proxima Centauri. Found using the radial velocity method in 2016, Proxima Centauri b is located just over 4 light-years away. This exoplanet is in the habitable zone of its star and has a mass similar to Earth's. Its proximity to our solar system makes it a prime candidate for future studies and exploration. The discovery of Proxima Centauri b has sparked excitement about the possibility of visiting or sending probes to study this nearby world. The search for exoplanets goes beyond finding planets similar to Earth. Scientists have discovered a wide variety of exoplanets, ranging from gas giants many times the size of Jupiter to rocky planets smaller than Earth. Some exoplanets orbit their stars at scorching distances, while others are in icy orbits far from their stars. This diversity has expanded our understanding of planetary systems and challenged previous assumptions about planet formation. The discovery of exoplanets has profound existential implications. It stirs our curiosity about the potential for life beyond Earth and our place in the universe. Finding a planet with conditions suitable for life raises the possibility that we are not alone. Even if we do not find direct evidence of life, discovering habitable exoplanets broadens our perspective on where life might exist and how it might arise in different environments. These discoveries also fuel the hope of finding a second Earth, a planet where humans might one day live or visit. The idea of colonizing other planets has long been a staple of science fiction. But the discovery of potentially habitable exoplanets brings this dream closer to reality. Advances in technology and space exploration may one day allow us to reach these distant worlds, furthering our understanding of the universe and our place within it. The search for exoplanets also inspires technological and scientific innovation. The development of more advanced telescopes and detection methods has been driven by the desire to find and study these distant worlds. Missions like the Transiting Exoplanet Survey Satellite, TESS, and the James Webb Space Telescope, JWST, are designed to expand our capabilities in this area. TESS, for example, is surveying the brightest stars near Earth for transiting exoplanets, while JWST will provide detailed observations of exoplanet atmospheres, looking for signs of habitability and even potential biosignatures. The invisible forces of the universe. Dark matter and dark energy are two of the most mysterious and intriguing concepts in modern astrophysics. Together, they make up about 95% of the universe, yet they remain largely unseen and poorly understood. These invisible forces play crucial roles in the structure and evolution of the cosmos, prompting ongoing research and deep philosophical reflections on the nature of reality. Dark matter was first proposed to explain observations that could not be accounted for by visible matter alone. In the 1930s, astronomer Fritz Zwicky noticed that galaxies in clusters were moving faster than expected based on the mass of visible stars. He suggested the presence of an unseen dark matter that exerted additional gravitational force. Later observations, such as the rotation curves of galaxies, supported this idea. Stars in the outer regions of galaxies were found to be moving at speeds that indicated more mass was present than what could be seen. Dark matter does not emit, absorb, or reflect light, making it invisible to current detection methods. However, its presence can be inferred through its gravitational effects on visible matter. For example, the bending of light from distant stars by galaxy clusters, known as gravitational lensing, indicates the presence of large amounts of dark matter. Additionally, computer simulations of galaxy formation and behavior require dark matter to match observed structures. Despite its pervasive influence, the exact nature of dark matter remains unknown. Various theories suggest it could be made up of exotic particles, such as WIMPs, weakly interacting massive particles, or axions, that interact weakly with normal matter. Experiments like the Large Hadron Collider and dedicated dark matter detectors aim to identify these particles, but so far, none have been directly detected. While dark matter binds galaxies and clusters together, dark energy is believed to be driving the accelerated expansion of the universe. This surprising discovery came in the late 1990s when astronomers studying distant supernovae found that these exploding stars were dimmer than expected, indicating they were farther away than previously thought. This led to the conclusion that the universe's expansion is not slowing down due to gravity but speeding up, propelled by an unknown force. Dark energy is even more mysterious than dark matter. It is thought to make up about 68% of the universe and acts as a repulsive force, counteracting gravity. One of the leading theories proposes that dark energy is related to the cosmological constant, a term Einstein included in his equations of general relativity to allow for a static universe, which he later abandoned. Another theory suggests it might be a dynamic field called quintessence, varying over time and space. The study of dark energy involves measuring the rate of the universe's expansion and how it changes over time. Projects like the Dark Energy Survey and the upcoming Euclid mission aim to map the distribution of galaxies and measure the expansion rate with unprecedented precision. By studying cosmic structures and their evolution, scientists hope to uncover the properties of dark energy and understand its role in the cosmos. The existence of dark matter and dark energy raises profound questions about the universe's nature and our place within it. These unseen forces dominate the cosmos, yet we have only a rudimentary understanding of what they are. This mystery fuels scientific curiosity and existential wonder, challenging us to explore the unknown and expand our knowledge. Dark matter and dark energy also highlight the limitations of our current theories. The standard model of particle physics, which successfully explains the behavior of known particles, does not account for dark matter. Similarly, general relativity describes gravity well, but does not fully explain the effects attributed to dark energy. These gaps suggest that new physics may be needed, potentially leading to groundbreaking discoveries and a deeper understanding of the universe. The search for dark matter and dark energy also underscores the interconnectedness of science and philosophy. As we probe the fundamental nature of the cosmos, we encounter questions about the limits of human knowledge and the nature of reality itself. What is the true nature of the universe? Are there aspects of existence that lie beyond our current understanding? These questions inspire both scientific inquiry and philosophical reflection, driving us to seek answers in the vast expanse of the cosmos. Moreover, the study of dark matter and dark energy has practical implications for our understanding of the universe's future. The balance between these forces will determine the ultimate fate of the cosmos. If dark energy continues to dominate, the universe could expand forever, leading to a cold, empty state known as the Big Freeze. Alternatively, changes in dark energy could result in different scenarios, such as a Big Rip, where galaxies, stars, and even atoms are torn apart. Understanding dark matter and dark energy is crucial for constructing a complete picture of the universe. These enigmatic forces shape the cosmos on the largest scales, influencing the formation of galaxies, clusters, and the overall structure of the universe. The anthropic principle. The universe fine-tuned for life. The anthropic principle is a philosophical concept that suggests the universe appears to be fine-tuned for the existence of life, particularly human life. It proposes that the fundamental constants and laws of physics are such that they allow for the development of life as we know it. The principle can be framed in different ways, leading to various interpretations and debates among scientists and philosophers. The anthropic principle comes in two main forms: the weak anthropic principle, WAP, and the strong anthropic principle, SAP. The weak anthropic principle states that the conditions observed in the universe must allow the observer to exist. In other words, we see the universe as fine-tuned for life because if it were not, we would not be here to observe it. This principle is essentially an observation about the necessity of life-compatible conditions for observers to exist. It does not imply that the universe is designed or intended for life, merely that our presence as observers is contingent on the universe having properties that support life. The strong anthropic principle goes a step further, suggesting that the universe must have properties that make the emergence of life inevitable. This interpretation implies that the universe is in some way compelled to develop life, and that these life-supporting conditions are not merely a coincidence. Proponents of the strong anthropic principle argue that the universe's physical laws and constants are not arbitrary, but are set in such a way that life must eventually arise. One of the key discussions surrounding the anthropic principle is why the universe appears to be fine-tuned for life. Several fundamental constants in the universe, such as the gravitational constant, the strength of electromagnetic forces, and the cosmological constant, seem to fall within very narrow ranges that allow for the formation of stars, planets, and ultimately life. If these constants were even slightly different, the universe could be vastly different and likely inhospitable to life. For example, if the gravitational constant were a bit stronger or weaker, stars might not form properly, or they could burn out too quickly to support the development of life on surrounding planets. Similarly, if the strength of the electromagnetic force were altered, chemical bonds might not form correctly, preventing the complex chemistry necessary for life. These precise conditions give the impression that the universe is finely tuned, sparking discussions about the reasons behind this apparent fine-tuning. One explanation for this fine-tuning is the idea of a multiverse, where many universes exist with different physical constants and laws. In this view, we happen to live in a universe where the conditions are right for life, but countless other universes might exist where the conditions are not suitable for life. The multiverse hypothesis suggests that our universe is just one of many, and the fine-tuning we observe is a result of our particular universe being one of the few where life can emerge. Another perspective is the idea of a deeper underlying principle or theory that explains why the constants have the values they do. This would mean that the observed fine-tuning is not a coincidence, but a result of a fundamental law of nature that we have yet to discover. Scientists continue to explore this possibility, seeking a unified theory that could account for the values of these constants. The anthropic principle also leads to philosophical reflections on the nature of the universe and our place within it. It raises questions about the significance of life and the human experience in the vastness of the cosmos. If the universe is fine-tuned for life, what does that say about our role in the universe? Are we a rare and significant occurrence, or just one of many possible outcomes in a multiverse? These questions touch on deeper existential themes, such as the meaning of life and our relationship with the cosmos. The idea that the universe is fine-tuned for life can inspire a sense of wonder and curiosity about the underlying reasons for our existence. It encourages us to explore the nature of the universe more deeply, seeking to understand the forces and principles that have shaped our world. The ultimate fate of everything. The ultimate fate of the universe is a profound question that has fascinated scientists and philosophers for centuries. Several theories have been proposed to describe how the universe might end, each based on different aspects of cosmological observations and physical principles. These theories include the Big Freeze, the Big Rip, and the Big Crunch, each offering a unique vision of the cosmos's final destiny. One of the most widely discussed scenarios is the Big Freeze, also known as the heat death of the universe. According to this theory, the universe will continue to expand indefinitely. As it does, galaxies will drift further apart, stars will exhaust their nuclear fuel, and new star formation will gradually cease. Over extremely long timescales, existing stars will burn out, and black holes will eventually evaporate through Hawking radiation. The universe will become a dark, cold, and empty place, with temperatures approaching absolute zero. In this state, known as thermal equilibrium, all energy will be evenly distributed, and no thermodynamic work will be possible. The Big Freeze represents a slow, inexorable decline into a state of maximum entropy, where all processes cease, and the universe reaches a state of perpetual stillness. Another possibility is the Big Rip. This theory suggests that the universe's expansion, driven by dark energy, could accelerate to the point where it overcomes all forces holding matter together. In this scenario, galaxies, stars, planets, and even atomic structures would be torn apart. The rate of expansion would increase so dramatically that everything, from galactic clusters to the smallest particles, would be ripped apart in a finite amount of time. The Big Rip would culminate in a violent and catastrophic end, with the fabric of space-time itself being torn asunder. In contrast to the Big Freeze and the Big Rip, the Big Crunch proposes a cyclical model of the universe's fate. According to this theory, the expansion of the universe could eventually slow down and reverse due to the gravitational pull of all the matter it contains. If the density of the universe is sufficient to halt its expansion, the universe would begin to contract. Galaxies would move closer together, stars would collide, and temperatures would rise as everything is pulled into an increasingly dense and hot state. Ultimately, the universe could collapse into a singularity, a point of infinite density and temperature, mirroring the conditions of the Big Bang. Some versions of this theory suggest that the universe might then undergo a new Big Bang, leading to a cyclical process of birth, death, and rebirth. The concept of the heat death of the universe, integral to the Big Freeze theory, has significant implications. It suggests a future where all processes come to an end and the universe exists in a state of permanent stagnation. This idea challenges our understanding of time, change, and the nature of existence. The notion that the universe could reach a point where nothing ever happens again is both awe-inspiring and unsettling. Philosophically, the potential end of the universe invites deep reflections on the finality and meaning of existence. The Big Freeze, with its depiction of an eternal, unchanging state, prompts us to consider the impermanence of all things. It emphasizes the transient nature of life and the eventual decay of all structures, from the smallest organisms to the largest galaxies. This perspective can evoke a sense of humility and a greater appreciation for the present moment. encouraging us to cherish the fleeting beauty of the cosmos. The Big Rip, on the other hand, presents a more dynamic and dramatic vision of the end. It highlights the forces that govern the universe's expansion and the potential for these forces to lead to a sudden and violent conclusion. This scenario underscores the unpredictability and fragility of existence, reminding us of the immense power and mystery of the cosmos. The Big Crunch, with its cyclical nature, offers a different philosophical outlook. It suggests that the universe is part of an endless cycle of creation and destruction. This view aligns with certain philosophical and spiritual traditions that see existence as a continuous process of birth, death, and rebirth. The idea of a cyclical universe can provide a sense of continuity and renewal, contrasting with the finality of the Big Freeze and the Big Rip. Regardless of which theory ultimately proves correct, contemplating the end of the universe deepens our understanding of the cosmos and our place within it. It invites us to explore the fundamental forces that shape reality and to consider the long-term implications of these forces. The study of the universe's fate also encourages us to reflect on the nature of time, change, and existence, fostering a greater appreciation for the mysteries and wonders of the cosmos. The role of consciousness. The nature of consciousness and its role in the cosmos is a profound and complex subject that continues to intrigue scientists, philosophers, and thinkers. Various theories attempt to explain the connection between consciousness and the universe, each offering unique insights into the fundamental aspects of reality. One such theory is panpsychism, which posits that consciousness is a fundamental and pervasive feature of the universe. Panpsychism suggests that all matter, not just living organisms, possesses some form of consciousness or subjective experience. According to this view, consciousness is not an emergent property that arises only in complex systems like human brains, but rather an intrinsic quality of all physical entities. This means that even the smallest particles, such as electrons or quarks, have a basic form of awareness. Panpsychism challenges the traditional materialist view that consciousness is solely a product of neural activity in the brain, proposing instead that it is a universal characteristic. One of the prominent proponents of a theory linking consciousness and the cosmos is Roger Penrose, a renowned physicist, and Stuart Hameroff, an anesthesiologist. Together, they developed the Orchestrated Objective Reduction, OR theory. This theory combines principles from quantum mechanics with insights from biology to propose a model of consciousness that is both scientifically grounded and profoundly intriguing. According to OR, consciousness arises from quantum processes occurring within the brain's microtubules, which are structural components of neurons. Penrose and Hameroff suggest that these microtubules function as quantum computers, capable of processing information in ways that classical computers cannot. They propose that the collapse of quantum states within the microtubules leads to moments of conscious awareness, a process they call objective reduction. This theory bridges the gap between the physical workings of the brain and the subjective experience of consciousness, offering a potential explanation for the nature of conscious thought. OR theory also posits that consciousness is not confined to biological organisms. If quantum processes in microtubules can give rise to consciousness, similar processes might occur in other structures throughout the universe. This idea aligns with the principles of panpsychism, suggesting that consciousness could be a fundamental aspect of the cosmos, present in various forms and degrees across different entities. The exploration of consciousness and its connection to the universe invites deep existential reflections. If consciousness is indeed a fundamental aspect of reality, it challenges our understanding of what it means to be alive and aware. It suggests that our individual experiences are part of a larger interconnected web of consciousness that permeates the cosmos. This perspective can lead to a greater sense of unity and interconnectedness with the universe, as well as a deeper appreciation for the complexity and mystery of existence. The idea that consciousness might be a fundamental aspect of the universe also raises questions about the nature of reality itself. If consciousness is not merely a byproduct of physical processes, but an intrinsic quality of matter, it implies that our understanding of the universe must account for subjective experience as well as objective phenomena. This challenges the traditional materialist view that seeks to explain the universe purely in terms of physical laws and mechanisms, suggesting instead that reality is a more intricate and multifaceted entity. Philosophically, the notion that consciousness is fundamental invites us to reconsider the relationship between mind and matter. It prompts us to explore how subjective experiences can arise from physical processes and how these experiences shape our understanding of the world. This exploration can lead to new insights into the nature of perception, cognition, and the self, as well as the ways in which consciousness interacts with the physical universe. The study of consciousness also has practical implications for our understanding of mental health and well-being. If consciousness arises from quantum processes within the brain, it suggests that our mental states are influenced by the fundamental workings of the universe. This perspective can inform approaches to mental health that consider not only the biological and psychological aspects of consciousness, but also its deeper quantum roots. Moreover, the exploration of consciousness and the cosmos has the potential to inspire technological advancements. Understanding how quantum processes give rise to consciousness could lead to the development of new forms of computing and artificial intelligence, as well as innovative approaches to harnessing the power of quantum mechanics. These advancements could revolutionize various fields, from medicine to technology to space exploration, opening up new possibilities for human progress and discovery. In contemplating the role of consciousness in the cosmos, we are reminded of the profound mystery and wonder that pervades the universe. The exploration of this mystery drives scientific inquiry and philosophical reflection, challenging us to expand our understanding of reality and our place within it. As we delve deeper into the nature of consciousness, we uncover new layers of complexity and interconnectedness, revealing the intricate and beautiful tapestry of existence. The study of consciousness also highlights the importance of interdisciplinary collaboration. Insights from physics, biology, psychology, and philosophy all contribute to a more comprehensive understanding of consciousness and its role in the universe. By bringing together different perspectives and methodologies, we can develop a richer and more nuanced view of this fundamental aspect of reality. Cosmic voids, empty spaces. While the universe is filled with billions of galaxies, stars, and planets, it is also characterized by vast regions of emptiness known as cosmic voids. These voids are some of the largest structures in the universe, yet they are almost devoid of matter. Understanding cosmic voids is essential for comprehending the large-scale structure of the universe and the forces that shape it. Cosmic voids are immense, spanning tens to hundreds of millions of light-years across. They contain far fewer galaxies, stars, and other forms of matter compared to the denser regions of the universe known as galaxy clusters and filaments. These voids are not completely empty. They contain sparse amounts of gas, dark matter, and a few isolated galaxies. However, their density is significantly lower than that of surrounding regions, making them appear nearly empty. The existence of cosmic voids was first suggested in the 1970s when astronomers began mapping the distribution of galaxies in the universe. Surveys revealed that galaxies were not evenly distributed, but rather formed a web-like structure with large, nearly empty regions interspersed between dense clusters and filaments of galaxies. This pattern, known as the cosmic web, is now understood to be a fundamental characteristic of the universe's large-scale structure. The formation of cosmic voids can be traced back to the early universe, shortly after the Big Bang. Initially, the universe was nearly homogeneous, with slight variations in density. These variations were imprinted in the cosmic microwave background, CMB radiation, the afterglow of the Big Bang. Over time, regions with slightly higher density began to collapse under gravity, forming the seeds of galaxies and galaxy clusters. Meanwhile, regions with lower density expanded and became more void-like, as matter was pulled away into denser regions. Cosmic voids continue to evolve over billions of years. As the universe expands, voids grow larger and more empty. This process is driven by the same gravitational forces that cause galaxies and clusters to clump together. The study of voids provides valuable insights into the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. By analyzing how voids grow and change over time, scientists can test theories about dark energy and improve our understanding of the universe's fate. One of the largest known voids is the Bootes void, also known as the Great Void. Discovered in 1981, the Bootes void is located approximately 700 million light-years from Earth and measures about 330 million light-years in diameter. It contains very few galaxies compared to other regions of similar size, making it one of the most significant voids known. The discovery of such a large void was initially surprising as it challenged existing models of the universe's structure. However, it has since been integrated into our understanding of cosmic evolution. Despite their emptiness, cosmic voids are not entirely devoid of interest or importance. They offer unique laboratories for studying fundamental aspects of cosmology and astrophysics. For example, voids provide a relatively clean environment for observing the effects of dark energy and testing theories of gravity. In denser regions, the interactions between galaxies and other matter can complicate such studies. Voids with their sparse matter allow for clearer observations and more straightforward interpretations. The study of cosmic voids also has implications for our understanding of dark matter. Dark matter, which makes up about 27% of the universe's mass energy content, is invisible and interacts primarily through gravity. By observing the distribution and dynamics of matter in and around voids, scientists can infer the properties and behavior of dark matter. For instance, the way galaxies are distributed around the edges of voids can reveal how dark matter influences their formation and motion. One of the fascinating aspects of voids is their potential to host unique astrophysical phenomena. Although voids contain fewer galaxies, the galaxies that do reside within them can be unusual. These galaxies, often referred to as void galaxies, tend to be isolated and have unique properties compared to their counterparts in denser regions. They can offer insights into how galaxy formation and evolution differ in low-density environments. Studying these galaxies helps astronomers understand the range of conditions under which galaxies can form and thrive. Voids also have a significant impact on the cosmic microwave background radiation. The CMB is the oldest light in the universe, dating back to about 380,000 years after the Big Bang. As CMB photons travel through the universe, they interact with matter and energy, including the gravitational fields of voids. These interactions can leave subtle imprints on the CMB, known as the Integrated Sachs-Wolfe (ISW) effect. By studying the ISW effect, scientists can learn more about the properties of voids and the expansion of the universe. The philosophical implications of cosmic voids are profound. The sheer scale and emptiness of these regions challenge our understanding of existence and our place in the cosmos. On a human scale, the idea of such vast, empty spaces can evoke feelings of insignificance and awe. The existence of cosmic voids reminds us that the universe is not just a collection of stars and galaxies, but also a place of immense emptiness and solitude. From a philosophical perspective, voids can be seen as a metaphor for the human experience of isolation and the search for meaning in a vast, often indifferent universe. The emptiness of voids contrasts sharply with the richness of life and activity on Earth, highlighting the rarity and preciousness of our existence. This contrast can inspire a sense of wonder and curiosity about the universe and our place within it. Moreover, the study of cosmic voids underscores the importance of perspective in understanding the universe. While voids might seem like empty, uninteresting regions, they play a crucial role in the cosmic web and the evolution of the universe. Similarly, our understanding of life, existence, and meaning can be enriched by considering different perspectives and exploring the vast, often overlooked aspects of reality. Cosmic voids also raise questions about the nature of the universe and the forces that shape it. The existence of these vast empty spaces challenges us to think about the underlying principles governing the cosmos. It invites us to consider how the universe can be both incredibly full and incredibly empty, and how these opposing qualities coexist and influence each other. In addition to their scientific and philosophical significance, cosmic voids also have a practical impact on our exploration of the universe. As astronomers map the distribution of galaxies and other structures, they must account for the presence of voids and their influence on observations. For example, voids can affect the apparent positions and velocities of galaxies, leading to potential biases in measurements. Understanding these effects is essential for accurate cosmological studies and for interpreting data from large-scale surveys. The future of humanity in space. The future of humanity in space is a topic that stirs both imagination and ambition. The possibilities and challenges of interstellar travel are at the forefront of discussions about our potential to become a multi-planetary species. The journey to other stars and planets presents a formidable set of obstacles, but also holds the promise of new horizons and the survival of our species beyond Earth. Interstellar travel, or travel between stars, is a daunting challenge due to the vast distances involved. The nearest star system, Alpha Centauri, is over 4 light-years away, meaning that even light, the fastest thing in the universe, takes more than 4 years to travel this distance. Current space travel technology is far too slow for interstellar journeys, as our fastest spacecraft would take tens of thousands of years to reach even the closest stars. One of the most promising ideas for overcoming these distances is the concept of the light sail. This involves using a large reflective sail that is pushed by the pressure of light from lasers or the sun. Projects like Breakthrough Starshot aim to send tiny, lightweight probes to Alpha Centauri using this technology. These probes could potentially reach speeds of up to 20% of the speed of light, reducing the travel time to just a few decades. While this approach holds promise, it requires significant technological advancements and massive infrastructure to generate the necessary power for the lasers. Another intriguing possibility is the development of nuclear propulsion. Nuclear-powered spacecraft could provide much greater speeds than chemical rockets by using nuclear reactions to generate thrust. Concepts like nuclear thermal propulsion and nuclear fusion propulsion are being explored, with the potential to dramatically shorten travel times within our solar system and potentially for interstellar missions. However, these technologies are still in the experimental stages and face considerable engineering and safety challenges. The challenges of interstellar travel extend beyond propulsion. Navigating and communicating across such vast distances present additional hurdles. Spacecraft traveling at high speeds would need to avoid collisions with even tiny particles, which could cause significant damage at such velocities. Additionally, maintaining communication with Earth over light years would require advanced systems to handle the delays and data transmission across these immense distances. Despite these challenges, the potential rewards of interstellar travel are immense. Reaching other star systems could open up new opportunities for exploration, discovery, and the expansion of human presence in the universe. The search for exoplanets has already identified many potentially habitable worlds, and traveling to these planets could allow us to study them up close and even consider the possibility of colonization. Becoming a multi-planetary species is a concept that has gained significant attention, particularly with the vision of colonizing Mars. Establishing a human presence on Mars would be a significant step towards ensuring the long-term survival of humanity. Mars offers a relatively accessible location with conditions that, while harsh, could potentially be adapted to support human life with the right technology. The implications of becoming a multi-planetary species are profound. Colonizing other planets could provide a safeguard against catastrophic events on Earth, such as natural disasters, pandemics, or other existential threats. By spreading humanity across multiple planets, we increase our chances of survival and continuity. This vision of a multi-planetary future also drives innovation and inspires new generations to pursue careers in science, technology, engineering, and mathematics. The idea of living on other planets raises important philosophical questions about human destiny and our place in the cosmos. It challenges us to think about what it means to be human and how we define our identity and culture in the context of new environments. The experience of living on another planet would fundamentally change our perspective, offering new ways of understanding and relating to the universe. Colonizing other planets also brings ethical considerations. We must carefully consider the impact of our presence on these new worlds, particularly if they harbor microbial life or unique ecosystems. The principle of planetary protection, which aims to prevent contamination of other planets and moons, becomes even more critical as we expand our reach. Respecting and preserving the natural environments of other worlds is essential to ensure that our exploration does not cause harm. Furthermore, the pursuit of space colonization highlights the importance of cooperation and unity among humans. The scale and complexity of space missions require collaboration across nations and disciplines. Working together to achieve common goals in space can foster a sense of global unity and shared purpose, transcending political and cultural differences. The philosophical implications of human destiny in space extend to our understanding of survival and adaptation. Throughout history, humans have shown remarkable resilience and ingenuity in the face of challenges. The drive to explore and push boundaries is a fundamental aspect of our nature. Space travel represents the next frontier in this journey, offering new challenges that will test our creativity and determination. Survival beyond Earth also prompts us to consider the long-term future of humanity. The exploration and colonization of other planets could span centuries, requiring sustained commitment and vision. This long-term perspective encourages us to think about the legacy we leave for future generations and the kind of civilization we aspire to build. The overview effect. The overview effect is a profound cognitive shift reported by many astronauts who have had the opportunity to view Earth from space. This phenomenon, first described by space philosopher Frank White in the 1980s, refers to the transformative experience of seeing our planet from a distance. It fundamentally alters an astronaut's perception of the Earth and their place within the universe. When astronauts view Earth from space, they see a small, fragile, and beautiful sphere suspended in the vastness of space. The thin blue line of the atmosphere, the swirling clouds, the vast oceans, and the varied landscapes come into view as a single, interconnected entity. This sight often evokes a deep sense of awe and wonder, as well as a powerful realization of the interconnectedness of all life on Earth. The psychological impact of the overview effect is profound. Astronauts frequently describe a sense of overwhelming emotion, ranging from euphoria to a deep contemplative tranquility. This shift in perspective leads to a heightened awareness of the planet's fragility and the urgent need to protect and preserve it. The view from space starkly contrasts with the daily experiences on the ground, where political, social, and economic divisions dominate our consciousness. From space, these divisions vanish, replaced by a holistic view of the Earth as a unified living system. The overview effect also has significant philosophical implications. It challenges astronauts to reconsider their beliefs and values, often leading to a renewed sense of purpose and responsibility. This shift in consciousness can lead to a more profound appreciation for the environment, a stronger commitment to peace and cooperation, and a deeper understanding of humanity's place in the cosmos. One of the key aspects of the overview effect is the sense of unity it fosters. Astronauts often speak of feeling a deep connection to all people and life forms on Earth. The boundaries that typically divide us, national borders, cultural differences, and personal identities, become insignificant when viewed from space. This perspective encourages a sense of global citizenship, where the well-being of the planet and its inhabitants takes precedence over individual or national interests. The transformative power of the overview effect can also inspire existential reflection. Viewing Earth from space prompts questions about the meaning of life, our purpose as a species, and our responsibility to future generations. It invites contemplation on the fragility of our existence and the preciousness of the biosphere that supports life. This reflection can lead to a deeper sense of interconnectedness and a more profound commitment to stewardship and sustainability. Several astronauts have shared their experiences of the overview effect, offering insights into how this perspective shift has influenced their lives and work. For example, Apollo 14 astronaut Edgar Mitchell described a sense of universal connectedness and an inner realization of the oneness of all life. He spoke of an instant global consciousness and a deepened sense of responsibility for the planet. Similarly, astronaut Chris Hadfield has eloquently described the emotional impact of seeing Earth from space. He noted the stark contrast between the serenity of the planet viewed from orbit and the chaos and conflict often reported in the news. This perspective inspired him to advocate for environmental protection and international cooperation. The overview effect has also been a catalyst for various initiatives aimed at fostering a sense of global unity and environmental awareness. Organizations like the Overview Institute and Space for Humanity work to promote the insights gained from space travel, aiming to extend this transformative experience to more people. These efforts seek to leverage the power of the overview effect to drive positive change on Earth, encouraging a more sustainable and harmonious relationship with our planet. In addition to its psychological and philosophical impact, the overview effect has practical implications for policy and decision-making. Leaders and policymakers who have experienced this shift in perspective may be more inclined to prioritize global issues such as climate change, biodiversity loss, and resource management. The holistic view of Earth from space can help inform more integrated and cooperative approaches to addressing these complex challenges. The overview effect also underscores the importance of space exploration and the value of making this perspective accessible to more people. As private space travel becomes more feasible, there is potential for a broader segment of humanity to experience this transformative view. By expanding access to space, we can cultivate a greater sense of global unity and environmental responsibility among diverse populations. Furthermore, the overview effect has implications for education and public awareness. By sharing the experiences of astronauts and promoting the insights gained from viewing Earth from space, educators and communicators can inspire a new generation to think more globally and act more sustainably. Visualizations and simulations of the Earth from space, such as those created by satellite imagery and virtual reality technology, can help convey the essence of the overview effect to those who have not yet had the opportunity to travel to space. The bizarre world of quantum mechanics. Quantum mechanics is a branch of physics that explores the behavior of particles on the smallest scales, such as atoms and subatomic particles. It reveals a world that is fundamentally different from our everyday experience, governed by principles that often seem bizarre and counterintuitive. The discoveries and principles of quantum mechanics have not only revolutionized our understanding of the microscopic world, but also have profound implications for the structure of the universe and our philosophical perspectives on reality. At the heart of quantum mechanics are several key principles. One of these is wave-particle duality, which states that particles such as electrons and photons can exhibit both wave-like and particle-like properties. For instance, light can behave as both a wave, which can interfere and create patterns, and as particles called photons, which can be counted and detected individually. This duality challenges the classical idea that something must be either a wave or a particle, showing that on the quantum level, entities can exhibit characteristics of both. Another fundamental principle is quantization, the idea that certain properties, like energy, can only take on discrete values. This was first introduced by Max Planck to explain blackbody radiation and later expanded by Niels Bohr to describe the energy levels of electrons in atoms. According to this principle, electrons can only occupy specific energy levels, and they must absorb or emit energy in discrete amounts or quanta to move between these levels. Quantum superposition is another core concept. It states that a quantum system can exist in multiple states simultaneously until it is measured. For example, a particle can be in a state where it is both spinning clockwise and counterclockwise at the same time. This principle is famously illustrated by the thought experiment known as Schrödinger's cat, in which a cat in a sealed box is considered to be both alive and dead until the box is opened and the cat is observed. Quantum entanglement is a phenomenon where particles become interconnected in such a way that the state of one particle instantaneously influences the state of another, no matter how far apart they are. This connection persists even when the particles are separated by vast distances, suggesting a level of instantaneous communication that defies classical physics. Albert Einstein famously referred to entanglement as spooky action at a distance, highlighting its seemingly paradoxical nature. The principles of quantum mechanics play a crucial role in the structure of the universe. On the most fundamental level, quantum mechanics governs the behavior of particles and forces, shaping the very fabric of reality. It provides the foundation for understanding atomic and molecular structures, the interactions between particles, and the behavior of matter and energy on the smallest scales. In the context of space and cosmology, quantum mechanics has significant implications. For example, the early universe, just after the Big Bang, was governed by quantum processes. Quantum fluctuations in the density of matter and energy are believed to have seeded the formation of galaxies and large-scale structures in the universe. These tiny fluctuations were amplified by cosmic inflation, leading to the diverse and complex cosmos we observe today. Quantum mechanics also plays a critical role in the behavior of black holes. The concept of Hawking radiation proposed by Stephen Hawking suggests that black holes can emit radiation due to quantum effects near the event horizon. This radiation causes black holes to lose mass and eventually evaporate over time. The study of black holes through the lens of quantum mechanics continues to be a rich area of research, providing insights into the fundamental nature of gravity and space-time. The philosophical implications of quantum mechanics are profound and far-reaching. The phenomena of quantum superposition and entanglement challenge our classical understanding of reality and causality. They suggest that the universe is not deterministic in the way classical physics implies, where the future is entirely determined by the present. Instead, quantum mechanics introduces an element of probability and uncertainty where multiple outcomes are possible until a measurement is made. Quantum entanglement, in particular, raises questions about the nature of information and communication. The instantaneous connection between entangled particles suggests that information can be shared across vast distances without any apparent medium or delay. This challenges our conventional notions of space and time, suggesting that they might be more interconnected than previously thought. The principle of superposition also invites philosophical reflection on the nature of reality. If particles can exist in multiple states simultaneously, it suggests that reality itself might be composed of overlapping possibilities. This idea resonates with various interpretations of quantum mechanics, such as the many worlds interpretation, which posits that all possible outcomes of a quantum event actually occur in separate parallel universes. Each measurement or observation splits the universe into multiple branches, each representing a different outcome. These philosophical implications extend to our understanding of consciousness and observation. In quantum mechanics, the act of measurement plays a crucial role in determining the state of a system. This has led some to speculate about the relationship between consciousness and the physical world. Does the observer play an active role in shaping reality? While such ideas remain speculative and controversial, they highlight the deep and often puzzling connections between the quantum world and our experience of reality. Ripples in the fabric of space-time. Gravitational waves are ripples in the fabric of space-time, predicted by Albert Einstein over a century ago as part of his theory of general relativity. These waves are generated by the acceleration of massive objects, such as when black holes collide or stars explode in supernova. Gravitational waves travel through the universe at the speed of light, carrying information about their origins and the nature of gravity itself. The existence of gravitational waves was confirmed on September 14, 2015, by the Laser Interferometer Gravitational Wave Observatory, or LIGO. This groundbreaking discovery opened a new window into the universe, allowing scientists to observe cosmic events that were previously undetectable. LIGO, with its twin detectors located in Washington and Louisiana, uses laser beams to measure tiny distortions in space-time caused by passing gravitational waves. The detection process involves splitting a laser beam into two perpendicular paths. These beams travel down long tunnels, reflecting off mirrors and then recombine. Under normal conditions, the beams cancel each other out due to their alignment. However, when a gravitational wave passes through, it slightly distorts the lengths of the tunnels, causing the beams to shift out of alignment and produce an interference pattern. This pattern is a signal that a gravitational wave has passed. The first direct detection of gravitational waves by LIGO came from the merger of two black holes about 1.3 billion light-years away. This event released an immense amount of energy, creating ripples in space-time that eventually reached Earth. The discovery was a monumental confirmation of Einstein's prediction, providing direct evidence of the existence of gravitational waves and supporting the validity of general relativity. Gravitational waves confirm several key aspects of general relativity. Firstly, they demonstrate that space-time can be curved and distorted by massive objects. The waves themselves are distortions that propagate through the universe, much like ripples on a pond. Secondly, the detection of gravitational waves from merging black holes supports the idea that these objects exist and behave as predicted by Einstein's equations. The waves also provide insights into the extreme conditions near black holes, where gravity is incredibly strong and space-time is highly curved. The significance of detecting gravitational waves extends beyond confirming theoretical predictions. It has profound implications for our understanding of the universe and our place within it. Gravitational waves offer a new way to observe and study cosmic events that are invisible to traditional telescopes. They allow us to hear the universe, capturing signals from cataclysmic events that produce gravitational waves, but little or no light. This new form of observation has already led to remarkable discoveries. For example, in 2017, LIGO and the Virgo detector in Italy observed gravitational waves from the collision of two neutron stars. This event, known as GW 170817, was also observed across the electromagnetic spectrum by telescopes around the world. The combined observations provided detailed information about the properties of neutron stars, the production of heavy elements like gold and platinum, and the dynamics of such collisions. This multi-messenger astronomy, combining gravitational wave and electromagnetic observations, offers a more comprehensive view of the universe. Gravitational wave astronomy is still in its early stages, but its potential is immense. By detecting more events and improving the sensitivity of detectors like LIGO and Virgo, scientists can explore a wide range of phenomena, from the mergers of black holes and neutron stars to the vibrations of the early universe. Future detectors, such as the space-based LISA, Laser Interferometer Space Antenna, will extend our ability to detect gravitational waves from even more sources, including those at lower frequencies. The discovery of gravitational waves has existential implications, prompting reflection on the nature of reality and our understanding of the cosmos. These waves are a direct manifestation of the dynamic nature of space-time, revealing that the universe is a constantly changing and evolving entity. The ability to detect and study gravitational waves adds a new dimension to our exploration of the universe, expanding our knowledge and challenging our perceptions. The detection of gravitational waves also underscores the power of human ingenuity and the collaborative nature of scientific discovery. LIGO's success was the result of decades of work by a global community of scientists, engineers, and institutions. It demonstrates the importance of perseverance, innovation, and international cooperation in advancing our understanding of the universe. The achievement of detecting these elusive waves is a testament to our capacity to overcome challenges and push the boundaries of knowledge. Moreover, gravitational waves provide a unique way to test the fundamental laws of physics. They offer an opportunity to probe the nature of gravity under extreme conditions, potentially revealing new insights into the behavior of space-time and the fundamental forces of nature. By studying gravitational waves, we can test general relativity in regimes where it has never been tested before, and explore whether there are deviations from Einstein's predictions that could hint at new physics. Exoplanets and the Goldilocks zone, habitable worlds. As our understanding of the cosmos has expanded, one of the most interesting areas of discovery has been the identification and study of exoplanets, planets that orbit stars outside our solar system. The search for these distant worlds has been driven by a fundamental question: are we alone in the universe? By finding planets that could potentially harbor life, we edge closer to answering this profound question. The term Goldilocks zone is often used to describe the habitable zone around a star, where conditions are just right, not too hot and not too cold, for liquid water to exist on a planet's surface. Water is considered essential for life as we know it, making the Goldilocks zone a prime target in the search for habitable exoplanets. Planets within this zone are neither scorched by their star's heat nor frozen in the cold reaches of space, creating a potential haven for life. Discovering exoplanets is a challenging task due to their vast distances from us and the blinding light of their parent stars. However, astronomers have developed several ingenious methods to detect these distant worlds. The most successful of these methods is the transit method, used by telescopes like NASA's Kepler Space Telescope. This method involves monitoring the brightness of stars for periodic dimming, which occurs when a planet passes in front of its star, blocking a fraction of its light. By analyzing the light curve, the graph of the star's brightness over time, astronomers can infer the presence of a planet, its size, and its orbital period. Another method, called the radial velocity or Doppler method, measures the star's wobble caused by the gravitational pull of an orbiting planet. As the planet orbits, it tugs on the star, causing it to move slightly. This movement changes the star's light spectrum due to the Doppler effect, allowing astronomers to detect the planet's presence and estimate its mass. Once exoplanets are detected, the next step is to determine if they lie within the Goldilocks zone of their parent star. This involves calculating the planet's distance from the star and understanding the star's characteristics, such as its size and luminosity. Stars come in various types, from massive bright O-type stars to smaller, cooler M-type red dwarfs. Each type has a different Goldilocks zone, with more massive stars having wider zones that are farther out, while smaller stars have narrower zones closer in. The diversity of exoplanets discovered so far is astounding. They range from gas giants like Jupiter to rocky planets similar to Earth, and even exotic worlds like super-Earths, rocky planets larger than Earth, and mini-Neptunes, smaller versions of Neptune. Some of these planets have extreme conditions, such as scorching temperatures, intense radiation, or thick atmospheres of gas. Yet among this diversity, scientists are particularly interested in Earth-like planets that might offer the right conditions for life. One of the most promising discoveries in recent years is the TRAPPIST-1 system, located about 39 light-years from Earth. This system consists of a small, cool M-type star with 7 Earth-sized planets orbiting it. Remarkably, 3 of these planets are within the star's Goldilocks zone, where conditions could allow for liquid water. The close proximity of the TRAPPIST-1 system and the number of potentially habitable planets make it a prime target for further study and potential exploration. The James Webb Space Telescope, JWST, launched in December 2021, has further enhanced our ability to study exoplanets. With its advanced infrared capabilities, JWST can analyze the atmospheres of these distant worlds, looking for signs of habitability and potential biosignatures, indicators of life. By studying the light that passes through an exoplanet's atmosphere during a transit, scientists can identify the presence of molecules such as water vapor, carbon dioxide, methane, and oxygen. The detection of these molecules could indicate that the planet has the necessary conditions to support life. While the discovery of exoplanets in the Goldilocks zone is thrilling, it is important to note that being in this zone does not guarantee habitability. Several factors influence a planet's potential to support life, including its atmosphere, magnetic field, geological activity, and history of water. For example, Venus and Mars lie within the Sun's Goldilocks zone, but Venus has a thick, toxic atmosphere with extreme greenhouse effects, while Mars has a thin atmosphere and a cold, barren surface. Therefore, finding a planet in the habitable zone is just the first step in assessing its potential for life. The study of exoplanets also opens up the possibility of discovering new types of life forms, different from those on Earth. Life as we know it depends on carbon-based molecules and liquid water. but there could be other forms of life that use different chemical processes. The discovery of extremophiles, organisms that thrive in extreme conditions on Earth, such as in acidic hot springs, deep ocean vents, and polar ice, suggests that life could exist in a wider range of environments than previously thought. This broadens the criteria for habitability and encourages the search for life in diverse and unexpected places. Exploring exoplanets and the Goldilocks zone challenges us to think beyond our own planet and consider the vast potential for life in the universe. It underscores the importance of developing advanced technologies for space exploration and observation. Missions like the Transiting Exoplanet Survey Satellite, TESS, the European Space Agency's Plato, Planetary Transits and Oscillations of Stars, and the planned LUVOIR, Large UV/Optical/IR Surveyor mission, aim to find and study more exoplanets, bringing us closer to answering the age-old question of whether we are alone. In addition to searching for habitable exoplanets, scientists are also exploring the possibility of human colonization of other worlds. Mars has been a primary focus of these efforts due to its relative proximity and the presence of water ice. NASA's Artemis program aims to return humans to the Moon and establish a sustainable presence by the end of the decade, serving as a stepping stone for future missions to Mars. The idea of creating a self-sustaining human colony on Mars involves numerous challenges, including developing technologies for life support, radiation protection, and sustainable resource utilization. Overcoming these challenges would not only ensure the survival of humanity, but also expand our presence in the cosmos. The search for habitable worlds and the exploration of exoplanets is not just a scientific endeavor. It also has profound philosophical implications. It challenges us to reconsider our place in the universe and the uniqueness of life on Earth. Discovering even microbial life on another planet would have a profound impact on our understanding of biology, evolution, and the conditions necessary for life. It would suggest that life is a common outcome in the universe, given the right conditions, and that Earth is not unique in its ability to support life. On the other hand, if we find that life is extremely rare or even unique to Earth, it would underscore the preciousness of our planet and the importance of protecting and preserving it. The vastness and emptiness of space remind us of the fragility of our existence and the need to cherish and sustain the only home we currently have. The largest structures in the universe. Galactic superclusters are the largest known structures in the universe, vast groupings of galaxies that span hundreds of millions of light-years across. These colossal formations are composed of smaller clusters and groups of galaxies, bound together by gravity, creating an intricate web of matter that extends through the cosmos. The study of superclusters provides valuable insights into the large-scale structure of the universe and the processes that have shaped it over billions of years. Superclusters form through the gravitational pull of dark matter and the subsequent clustering of galaxies. After the Big Bang, the universe began to expand and cool, allowing matter to clump together under the influence of gravity. Over time, these clumps grew larger, forming galaxies and clusters of galaxies. As these structures continued to evolve, they merged to create even larger formations, resulting in the superclusters we observe today. Dark matter plays a crucial role in this process, providing the additional gravitational pull needed to bind these massive structures together. One of the most significant superclusters is the Laniakea supercluster, which includes our own Milky Way galaxy. Discovered in 2014, Laniakea is an immense structure spanning about 520 million light-years and containing roughly 100,000 galaxies. The name Laniakea means immense heaven in Hawaiian, reflecting the vastness of this cosmic formation. The Laniakea supercluster is bound together by a common gravitational center, drawing galaxies toward a region known as the Great Attractor, which exerts a significant gravitational influence on the supercluster. The discovery of Laniakea and other superclusters highlights the complex and hierarchical nature of the universe. These structures are part of the cosmic web, a vast network of interconnected filaments and voids that spans the entire observable universe. The cosmic web is composed of galaxies, clusters, and superclusters, with dark matter providing the scaffolding around which these structures form. This intricate organization reveals a universe that is both highly structured and dynamic, constantly evolving under the influence of gravity and dark matter. The significance of galactic superclusters extends beyond their sheer size. They provide important clues about the distribution of matter in the universe and the influence of dark energy on cosmic expansion. By studying the distribution and movement of galaxies within superclusters, scientists can gain insights into the underlying properties of dark matter and dark energy. These observations help refine our understanding of the universe's composition and the forces that shape its large-scale structure. Galactic superclusters also prompt existential reflections on the scale and organization of the universe. The immense size of these structures challenges our ability to comprehend the vastness of the cosmos. The fact that our own Milky Way galaxy is just one of many within the Laniakea supercluster underscores the insignificance of our position in the grand scheme of things. It invites us to reflect on our place in the universe and the nature of existence within such a vast and complex system. The hierarchical structure of the universe, with galaxies grouped into clusters and clusters into superclusters, mirrors patterns observed in other natural systems. This fractal-like organization suggests that similar processes may govern the formation of structures at different scales, from the smallest particles to the largest cosmic formations. This interconnectedness highlights the unity of the cosmos and the underlying principles that shape its evolution. Understanding the scale of galactic superclusters also inspires a sense of awe and wonder. The enormity of these structures and the forces that bind them together reveal a universe that is far grander and more intricate than our everyday experiences suggest. This perspective can lead to a deeper appreciation for the beauty and complexity of the cosmos, encouraging us to explore and learn more about the universe we inhabit. The study of superclusters also raises philosophical questions about the nature of reality and our ability to perceive it. The vast distances and time scales involved in the formation and evolution of superclusters challenge our conventional understanding of space and time. They remind us that our perceptions are limited by our position within the universe and our current technological capabilities. This realization encourages humility and a recognition of the limitations of human knowledge, while also inspiring curiosity and the drive to push beyond those limits. Moreover, the existence of galactic superclusters underscores the interconnectedness of all things in the universe. The gravitational forces that bind galaxies into clusters and clusters into superclusters reflect a fundamental unity that permeates the cosmos. This interconnectedness can be seen as a metaphor for the interdependence of all life and matter, prompting reflections on the relationships between different parts of the universe and our role within it. In addition to their scientific significance, galactic superclusters offer a rich source of inspiration for art, literature, and philosophy. The imagery of vast cosmic structures and the interplay of gravity and dark matter have captured the imagination of people throughout history. These themes resonate with our innate desire to understand the universe and our place within it, fueling creative expression and intellectual exploration. As we continue to study galactic superclusters, we are likely to uncover new insights into the nature of the universe and the forces that shape it. Galactic superclusters are the largest known structures in the universe, formed through the gravitational influence of dark matter and the clustering of galaxies. The discovery of structures like the Laniakea supercluster highlights the complex and hierarchical nature of the cosmos, revealing a universe that is both highly structured and dynamic. The study of superclusters provides valuable insights into the distribution of matter, the influence of dark energy, and the underlying principles that govern the universe's evolution. I hope you enjoyed these facts. If you did, feel free to leave a like and subscribe to the channel. Thank you for watching.